So in this problem I'm going to talk about doing a momentum balance on a control volume. So I have our diagram shows that there is a shear stress moving in this direction at y and another shear stress yx moving at y plus delta y. So here's delta y. So you just have this point right here in the y plane and then delta y a little bit higher up in that plane, in the y plane. And you also have momentum of the fluid moving in this direction. So you have the momentum rho times Vx at point x right here, and then at point x plus delta x, here's our momentum rho Vx at x plus delta x. So we're going to do the momentum balance on this fluid that is moving in this direction. So the momentum balance is going to be the sum of the forces acting in this x direction is equal to the rate of momentum flow out at x plus delta x right here minus the rate of momentum flow in right here. So you're just going the total net this will be the total net momentum of the system. So the sum of the forces, first we'll calculate this. So in this case, this is not pressure driven flow. This is an example of a rectangular system where you have two parallel plates and one plate is moving in this direction to the right in the positive x direction. So the sum of forces in this case for the momentum balance is going to be your shear stress x in the yx at y plus delta y minus the shear stress in the y direction at point y. And all this is times delta x, delta z, because it's acting on this plane that's coming out of the paper and in the x direction. So this is delta x and delta z. So that's where the shear stress is acting. So these are our only forces, since there's no pressure driven flow. We don't have any pressure forces. There's no stresses due to pressure, just shear stress. What's the rate of momentum flow out? So the rate of momentum flow out is going to be Vx. This fluid is moving at a velocity Vx due to the sliding plate, and it's coming across the plane of change in y and change in z, which is coming out. So it's like a plane like this, and the momentum is moving in this direction. So it's the velocity moving across this area times your momentum value. So the flow rate times the momentum is the rate of momentum flow at this point. So I'm sorry, this is all for this flow out at x plus x, and so the flow in is going to be over here at Vx, change in y, change in z, equals the momentum at x. And so in this system we have a total momentum balance that looks like this, that you have your net shear stresses times the plane that the shear stress is acting on, as well as your rate of momentum, your net rate of momentum flow right here. So in this problem we can assume that Vx is constant in the x direction. So Vx is not changing anywhere in the x direction. So therefore Vx at x plus delta x is equal to Vx at x. If those two are equal, then that means there's no net momentum transport. So that whole right side of the momentum balance is going to be equal to 0. So remember, at the beginning of the class I named a few things that said that there's only going to be a net momentum transport in a few certain cases that we may go over, like changes in cross-sectional area, if we're looking at developing flows at entrances, or if we have porous walls. Other than that, I mean, if your velocity is constant, you should then automatically know there's not going to be any net momentum transport. So the right-hand side of the equation should be equal to 0. So if the right-hand side of the equation is equal to 0, momentum balance is now the sum of forces acting in the x direction is equal to 0. So again, our forces in this case is only our shear stresses. We don't have any pressure. It's not pressure-driven flow. So we found this as our forces earlier, If it's equal to 0, we can go ahead and divide by our control volume, change in x, change in y, change in z, and then take the limit as y goes to 0, and this becomes our governing equation saying that the shear stress gradient in the y direction is equal to 0. Now if we look at the other example that we started on in class where we do have a pressure-driven flow, we do have pressures on the side pushing this flow. So we have P at x and we have P at x delta x. We also have shear stresses as our forces. So if we do a momentum balance on this situation, again, sum of forces acting in the x direction equals our net momentum. Where again we're assuming that the pressure only varies in this in the direction of flow. So the pressure is only going to vary in this direction, and we know it's and we're going to assume also it's fully developed. So we know there's only one velocity component, and that's Vx. Vx only changes in the y direction. So Vx along the same y at y equals 0 or y equals h or whatever it may be, it's going to be exactly the same. So Vx at x is going to be equal to Vx at x delta x. So again, so there's no net momentum transport in this example either. So the sum of the forces acting in the x direction is 0. So this is your momentum balance. So what are our forces in this situation? Our forces are the pressures on the plane y delta x and shear stresses on the plane delta x delta y. So it's a little bit different than this other example earlier because we didn't have any pressures, but now we do. So we account for both of those forces on those planes. So now our sum of our forces are going to be equal to the pressure at x minus the pressure at x delta x times our plane, which is delta z delta y, plus our shear stresses as well. So this is the sum of our forces, and again our sum of our forces equals 0. So if we just move this to the other side, we have this equation. We divide by our control volume again and take the limits. We have this as our governing equation showing that the pressure gradient in the x direction is equal to the shear stress gradient in the y direction.